Hey everybody, it's still Doc. We're day 3, Calc 1, Lesson 9, Section 2.1 in the correct book. If you have the copy of the not correct book that we've been referring to at times, that's 2.7. I've actually done all 9 of these lessons in 2 days, so I'm still using this book. It's still the Sunday before our class even started. So, hopefully, by the time I assign your homework for this, I will have the correct numbers for you. If not, we'll figure something out. So, here we go. Oh, there's the word I've been waiting for. Derivatives and rates of change. So, rates of change are exactly that, derivatives. Anytime you have any type of rate, it can be measured by a derivative. So if you go back and you remember the first day I asked you to watch the mathematical model of the coronavirus, you probably heard a lot of things about rates of change there. Now we're going to start taking a look at them. Tangents, we already looked at, is finding the slope. Here's the slope formula, y sub 2 minus y sub 1, x sub 2 minus x sub 1 that we learned in high school. And then here we have our secant line, and we're developing our slope to find out how steep it is or what our rate of change is. Now, the tangent line to the curve at the specific point with the line through P, if I look at combining a limit, what we just learned, to that slope formula, then I get closer and closer and closer to that value. I then can find my slope or my rate of change by using limits. Provided that the limit exists, of course. So let's go back and let's take a look at the problem that we did a while ago. And here we have our parabola. And we're looking at 0.11, and we want to find the equation to the tangent line. So we know we have a equals 1 here. How do I know that? Well, my x value is 1. So that's what I'm going to take my limit to. Whatever my x value is here. So I have my f of x minus f of 1 over x minus 1. I plug that in just like I did before. I also factor and reduce just like I did before. And now I get down here and I realize that I can plug my 1 value in, and I do in fact get the slope of 2. So now I can use that 0.11 that they gave to us and that slope of 2, use the point slope formula. Reminder over here of the point slope formula. Y minus y sub 1 equals slope times x minus x sub 1. Very important. That's a formula you should just be able to pull out of your brain. If you don't, write it on a 3x5 card, put it by your bed, study it for a week. Okay. Sometimes we refer to the slope of the tangent line to a curve as the point, at the point, as the slope of the curve of the point. Okay, so the idea here is, if we took this point and we zoomed in, you can see this window is 2, 2 right here. If I start zooming in, the more that I zoom in, the more this begins to look like a straight line. So that's why you'll hear it, that kind of description. Okay, so now, again, we're still talking about the same thing, but we're going to look at it in a little different way. Another expression for finding the slope. Sometimes this is an easier expression. Sometimes it's not. So if we know that h is x minus a. Now, h, x minus a. X is the point that I'm looking at. A is the point that I'm wanting to approach to. This distance here. And then I have x equal a plus h. Then the slope of the secant line then will take this form. F of a plus h minus f of a over h. These two formulas are the same. When I put as a limit approaches 0, what I'm saying here is that the distance between my x values are getting closer to 0. That's the difference. Okay? Notice it's h approaches 0 in the formula, no matter what point we're looking at. That's because now, instead of doing it according to the limit as it approaches that point, we're doing it according to the limit as if there is no space between the distance between, well, approaching no space between the distance and the x's. So let's take a look at an example. We're going to look at y equals 3 over x, then find the slope of the tangent line. Okay, here. I'm using this formula that I just showed you. Okay, so actually, I think I'm going to write this out. Might be a little easier to follow. So let's see. Let f of x equal 3 over x. Okay, and we want the slope of the tangent line at 3, 1. This time I'm going to use my other formula. So I'm going to write it down here. I have my slope equals the limit as x approaches 0. Now notice my x point is 3, but I'm looking at as x, or actually h, I'm sorry. H approaches 0 because that h value, what that does is it shows that there's approaching no distance between the value that we want and the value that we're examining to look closely at. Okay, so that's the first part of our formula. As h approaches 0, we have f of a plus h minus f of a all over my h. All right, so let's start plugging in what we know. We have the slope, limit as h approaches 0. F of the a value is our 3. So we have 3 plus h minus f of 3 all over h. Now that I have that, I'm going to substitute my values into the function in question, which is 3 over x. So I have 3 over 3 plus h minus, if I substitute 3 in for x, I get 1. And then on the bottom, I still have h. And again, it's still the limit as h approaches 0. And obviously, I can't substitute that in. Now what I want to do is I need to combine these two. So in order to combine these two, I need to change this 1 to be a value with a common denominator. So this 1 then is going to become 3 plus h over 3 plus h. Anything over itself is 1. Now I can simplify that to be the limit as h approaches 0 of 3 minus h all over 3 plus h over h. So all I did here was say 3 minus, so I have to distribute this negative 3 minus h, all of that over 3 plus h. So here I see that the 3's do cancel, gone, and then I have negative h over 3 plus h, and it's divided by h, so I can invert and multiply here, and I see it reduces. So now that I have limit as h approaches 0, 1 over 3 plus h, and I can substitute in my 0, and I will get 1/3. Oh, negative 1/3. Forgot the negative. Sorry. Okay. All right. So we have the negative. All right. So I was looking at this earlier. I said, well, can I do it the other way? Well, let's do it the other way and see the way that we did before. So now we're going to compare what we just did with our other formula. We know that we have 1/3. Let's look at the other formula. The other formula was slope equals limit as x approaches a, f of x minus f of a over x minus a. Now, in my problem, if I recall, if I look back up here, I see that my point is 3, 1. So let's get our problem down here where we can see it closer again. We have f of x equaling 3 over x, and we're looking at the slope of the tangent line at 3, 1. Okay, so if I'm going to do my problem this way, and I'm going to move this up for a little bit and then we'll compare in a while. If I'm going to do my problem this way, then when I fill it in, I will have my slope limit as x approaches 3, f of x minus f of 3 over x minus 3. Let's see what that does. Okay, so my f of x is 3 over x. My f of 3, if I plug 3 in, I will get 1 over x minus 3. Now again, this limit is as x approaches 3 because I'm using the point. I need to find a common denominator again. So I have x over x. 3 minus x over x minus 3. Now, when I take a look at 3 minus x over x, and I invert and multiply, I can see if I factored out a negative, that I could actually reduce these two. Okay, so this simplifies things, saying the limit as x approaches 3 of negative 1 over x is negative 1/3. And that is what we got up here. So here this shows you that both of those methods would work. Now, sometimes both of the methods won't work. That's why we often have different strategies. If we can't do something one way, we do it another way. Okay, that's life. So I just wanted to show you, though, how those two work out to be able to be the same. All right. Okay, so one of the things that the second formula is used for is velocity. So here we have the problem that we talked about before, where we have the ball being dropped from the observation deck of the tower 450 meters above the ground. We are wanting to find the velocity or instantaneous velocity at a specific time. That time will be our a value. Okay, t equals a, and we'll need to know the limit of the average velocities. So question is, what is the velocity of the ball after 5 seconds? And how fast is the ball traveling when it hits the ground? So I'm going to rewrite this problem so we can do it here. We know from our equation before, oh, I need another piece of paper. There we go. From our equation before that we have f of t equaling 4.9 t squared. So if we use our new formula, we're looking at, for velocity at a, we're looking at the limit as h approaches 0, which again means that I am getting so close that there's really no space in between the limit of what I'm looking at, or not no space, but very little space between the limit of what I'm looking at and the actual number. So I have f of a plus h minus f of a. All of that over h. And if I substitute in my values, then I have my limit as h approaches 0. I'm going to substitute this in for t. So I have 4.9 a plus h squared minus f of a. So if I just plug my a in, 4.9 a squared. Okay, all of this is over h. So now I have my limit as h approaches 0. Binomial square again. I keep telling you, you need to know this, so hopefully you do. A squared, h squared, multiply together and double it. We have 4.9 here and minus 4.9 a squared still here from our formula. All of that over h. Okay, as I continue to solve that, I'm going to distribute my 4.9 in. When I distribute my 4.9 into my value, then I have 4.9 a squared plus, we have 49 and 49, so that'll be 98, 9.8 AH plus h squared minus 4.9 a squared, which makes me happy because in the next step I can cancel these. Remember, canceling is when you're eliminating. All right, so now I can factor out my h value. Oh, not here because I factored it out. And I can reduce. Okay, so now I have my limit as h approaches 0. 9.8 a plus h, and I can substitute in my 0 for h, and I get my limit of 9.8 a. Okay, so that wasn't so bad, hopefully. All right, so what does that mean? Well, that gives us our formula. So now we have to find the velocity after 5 seconds. So I'm going to go back and I'm going to put 5 into my value. So I'm going to have 9.8 times 5, because this is my velocity formula after 5 seconds. That's what we solve for, velocity after 5 seconds. Velocity is a rate of change. Okay, so then when I multiply that together, I will get 49 meters per second. Okay, that's after 5 seconds. Now, what about when it hits the ground? We know that it's 450 meters above the ground because that was given to us. So we want to know, will the ball hit the ground at the time t, when s of t equals 450? In other words, when does this equal 450? When does this function, which represents my distance, equal 450? Because when it does, it hit the ground. So when I solve for that, I'm going to take a look at dividing by 4.9, so, and taking the square root. Now I can ignore the negative because we're talking about time. Okay, that's where you have to use your common sense. All right, So now that I have this, I can find out what my velocity will be when it hits the ground. And you'll want your calculator for this. (9.8) times the square root of 450 over 4.9. And when I put that in my calculator, I find out that it's going 94 meters per second when it hits the ground. Okay? So there we go. All right. Now, ta-da, we finally get to say welcome to derivatives. So this tells us that we've seen the slope of a tangent line and the limits and form of this, and we find out that this is in fact the definition of a derivative of a function at the number a is in fact this formula. Likewise, if we have the value of a and we're approaching the value of a like I showed you in the example, this is also a definition of the derivative. So let's take a look at example 4, and we're going to use example 4 using this formula. So let's write down this formula first. This time I'm using the notation for derivative right here. Okay, and my example 4 question is find the derivative of x squared minus 8x plus 9 at a. Now, you might think, well, why are we finding the derivative? Why would we want to find the derivative? Remember what it represents. It represents a rate of change. It might be a velocity. It might be it might be any type of rate that you're looking for. A change, medication in the bloodstream, anything. So it's important, but now we're going to go back to generic equations for a little bit, just to get you used to this definition of the derivative. And here we have, again, our formula, and now we're going to plug it in. So if I plug this in, wherever there's an x, I'm going to put a plus h. Now, you might say, wait a minute, didn't we do that before? We did do this before. We did it just as an algebra problem on day 1. Now we're actually going to use it for what it is intended, which is a derivative. So if I have f of a plus h quantity squared minus 8 times a plus h plus 9. And I'm going to simplify that, another binomial square, a squared, h squared, multiply them together and double it. Here we go. Factor through the negative 8, minus. Okay. So here's what I have here. It doesn't look like anything combines. So I go on to the next one, which is f of a. So I have f of a now I'm subtracting the 2. So I take my result in this one, which is a squared plus 2ah plus h squared minus 8a minus 8h plus 9 minus, now distribute your negative through here, so we're going to be changing signs, a squared plus 8a plus, oh, see, I said it and then I almost forgot it, minus 9. That's why you guys have to keep me on my toes. All right. So here we go. Let's see what happens. Well, we're happy because some things cancel. This cancels. My a squares cancel. My negative 8a and my positive 8a cancels. My 9 and my negative 9 cancels. And that simply leaves me with 2ah plus h squared minus 8h. Okay, well that is all over my h. I have to go back to my formula and remind myself what I'm doing. I'm still looking at the limit as h approaches 0 of this function. I still can't substitute it in, but what I can in fact do is factor out an h. When I do that, I can reduce it with the one at the bottom. And there, ladies and gentlemen, is my derivative of this function. Okay? Now, of course, when I'm looking at actual derivative, I'm going to go back and put x in. So it would actually be 2x minus 8. Okay? All right. Questions? Now, they remind you, after that, for finding the equation of the tangent line, you will need to always know how to use the point-slope formula. And the point-slope equation can be written also, let's see, y minus y sub 1 equals m times x minus x sub 1. That can be written as y minus f of a equals my f prime, that's what we call this, f prime of a, times x minus a. So this is now that we have defined slope being a derivative. We can also say this, our y is just f of a, my x is just a, and this is another way to write our point slope formula. So if we go back and we look at example 4 and we say, well, let's find the slope of a tangent line in this problem. Here we didn't have a specific point, but we have an equation. So let's find the tangent line to this parabola at a specific point, and that is example 5. So example 5 says you have the same equation. You know the slope is going to be 2x minus 8. Now, what I want you to do is find the equation of a tangent line at the point 3, negative 6. So since it's at the point 3, negative 6, the first thing you're going to do is say, okay, well, this is my f prime of a. I put slope up here, but you can interchange them. Equals 2a minus 8. This is at 3 because that's my x value. And I find out that my slope is going to be negative 2. Okay, so I plug that in and I get a slope of negative 2. So the equation of the tangent line now, again, I have y minus y sub 1 equals m times the quantity x minus x sub 1, or written using the f of a values, the function notation here. Okay, so either way, y minus negative 6 equals negative 2 times x minus 3. And of course I want to simplify that, so when I subtract 6 from both sides, I just get negative 2x, which is a line of a slope of negative 2 that goes through the origin. That is, in fact, my tangent line going through that point. So here it is. Here is my parabola that I worked on. There is my point 3, -6. Here is my tangent line, which has a slope of -2. Okay? All right, now we're really moving along. This is good stuff. Now we're going to just talk about different things that derivatives are used for. We're going to talk about instantaneous rate of change, and it's all the same thing, guys and girls. It's all the same thing, but it's just different notation. So, Law 6 says, if I have a limit as delta x approaches 0, delta y over delta x. Hopefully you remember from algebra, delta y over delta x is just your slope. It's another way of writing slope. That's going to equal your limit as one point approaches the other point. Here is your slope formula again. All over x2 minus x1. Okay, so this takes us to looking at rates of change, and hopefully you remember from algebra class, your teachers probably taught you that delta y was the change in our y values, or y2 minus y1, and delta x are the change in your x values. Again, slope. So when we're looking at rate of change, we're looking at a limit as the delta x approaches 0. So that means delta x, again, is the distance from the point that you're looking at to a point close to it. Again, this is the same that we've looked at before. It's just different notation. So if we take a look at instantaneous rate of change, back to the book for a moment. We have instantaneous rate of change, which is called the average rate of change of y with respect to x over a specific interval. Can be interpreted as the slope of the secant line. So here we have our curve, here's our secant line, and we have our points, and we have our second point, and then we plug it in, and that's our instantaneous rate of change, which again, this is the same thing that we've been doing. It's just another way of applying it. Let's take a look at example 7. All right, example 7. Let DT be the U.S. national debt at time t. The table in the margin gives the approximate values of this function by providing end-of-year estimates in billions of dollars from 1980 to 2005. Interpret and estimate the value of D prime at 1990. So here we have our values. This is our time. Here's our years, and here are our values. Okay. So we take a look at our prime. We're looking at the limit as t approaches 1990, dt minus d at 1990, t minus 1990. So we can compute and tabulate the differences in the table. Here, if we go ahead and we plug these in, we will see that our slopes, our rates of change a little bit over time. So if we take a look at 1990, we get about $303 billion per year. Anytime you see per, that's indicating the rate of change, and that indicates slope, which indicates calculus. Okay, that is actually all for this lesson. And I will talk to you soon.